Authored by veteran chemistry teacher Abdul Shakur, these two textbooks provide all the essentials that would not only enable students to master grade 11 chemistry, but to excel at the next higher level in this subject. What make these texts unique are their creativity and profundity with which concepts are explained for clarity and mastery. The following is one of a set of 44 different tutorials created by the author, using materials primarily from the text Chemistry 11 in Focus. I hope you enjoyed this video. If you liked it, please give it a thumbs up and don't forget to subscribe. We will see you in the next video and thank you for watching.
Our tutorial today deals with the gaseous state and atmospheric pressure. It starts on page 320 and it ends on page 324. And the concepts that will be covered today are as follows: the gaseous state, units of atmospheric pressure, demonstration of atmospheric pressure. But first of all, we'll talk about atmospheric pressure effects. We have not studied atmospheric pressure as of yet, but we will in due course. However, I just want you to accept the fact that there exists a pressure that is being exerted upon us by the column of air in the atmosphere called atmospheric pressure. So if you observe here, we're having the earth, and all over above us is this column of air here that we call the atmosphere, and it is exerting a pressure on us that's called atmospheric pressure. We do not feel this pressure squeezing on us because it is believed that the combined pressures of our blood and that of the osmotic pressures of the other tissues of our body are equal and opposite to that of the atmosphere at sea level. However, a barometer, the instrument that's used to measure atmospheric pressure, showed that the atmospheric pressure decreases with height. The higher up into the atmosphere, the less is the pressure measured there. In other words, if a barometer is used to measure the pressure at this point here, it will measure a certain pressure that will, if it's at sea level, we'll call that 1 atmosphere. It's approximately about 100 kilopascal. If you place the barometer somewhere here, it will show a pressure that's much less than what it read at this point here. And again, if you go higher up into the atmosphere, it will show smaller and smaller pressures, okay? So as you go higher into the atmosphere, the pressure gets less and less. One of the questions I will normally pose to my student is this: what will happen with people if they're placed in a hot air balloon and they're taken up into the atmosphere to indefinite heights? You take them higher and higher into the atmosphere. What will eventually happen to the people in the air balloon? Some of the answers I will get are there'll be breathing problem, there'll be less oxygen as you go higher up into the atmosphere for you to breathe. Okay, people are supplied with cylinders of oxygen. What else might happen? They will feel cold, okay? They're provided with warm blankets. What else might happen? They will feel hungry. They are provided with food. What else? Then they will run out of responses. The answer to that is that the people within the air balloon will eventually die because of a number of reasons. One, there will be bursting of the blood vessels in the eyes, nose, and brain, and they eventually suffer from strokes. And not only that, they will suffer from something called gas embolism. All of a sudden, bubbles of gas will arrive in their blood vessels because of a low pressure there. Nitrogen bubbles will start to appear in the blood vessels that can affect circulation to the brain and everything like that. And that's why eventually these people will die. So why does that happen? You see, at sea level, it is the atmospheric pressure that is exerting upon us that keeps our blood vessels from bursting. However, as we ascend into the atmosphere, because the pressure gradually decreases there, our blood pressure and those of other tissues get comparatively greater than that of the atmospheric pressure. So with no adequate atmospheric pressure to oppose our blood pressures as we ascend, our blood vessels, for example, will burst. Something similar to that happens to the air pressure as we ascend into the atmosphere in an aircraft. To compensate for the decline in air pressure and oxygen, the pressure within the cabin is increased in a commensurate way. Also, more oxygen is supplied with the air to make breathing easier. This increase in pressure within the cabin is experienced by the popping of our eardrums. The following figures depict how this popping happens. This figure here shows that we are having a middle ear, which is an airtight cavity. It has an eardrum that separates it from the outer ear, and a closed eustachian tube that separates it from the mouth. So this here is an airtight cavity. Now let's see what happens during ascension. During ascension, as the pressure within the aircraft is increased in a commensurate way to compensate for the decline during ascension. So during this time, it causes the eardrum to be pushed inside. The increase in pressure here causes this eardrum to be pushed like that, and that is what is felt as a popping effect. So what they advise people to do is this. They advise you to counteract this effect by performing the swallowing act. Every time you swallow, this eustachian tube here, normally closed, opens up. And when that opens up, it allows air to flow in and out of this middle ear that is normally sealed. So in this case, because the outside pressure was greater or is greater than the inside pressure here, air moves from the mouth through the eustachian tube into the middle ear, where it equalizes the pressure inside here, so the eardrum now goes back to its original position. Okay? Now, let us see what happens during descent. This figure here shows what happens during descent. During descent, the pressure within the aircraft or the cabin is now decreased. As this happens, the eardrum is pushed outward because look what happened. When we are at the top of the descent, the pressure inside here was greater. But now because the outside pressure is getting less, the pressure here and the pressure within the mouth is getting smaller and smaller, this pressure here relative to the pressure outside is greater, and now the eardrum pops in the other direction. See? And again, the swallowing act is recommended. When you do the swallowing act now, it causes the eustachian tube here to open, and any excess pressure inside here is equalized by the movement of the air from within the middle ear to the outside. And that is how the popping effect happens, and these are some of the tips that you can carry out to minimize the discomfort that is felt during the ascent and descent. One of the questions that was asked here, I implore you to read the information given here, all right? You can pause the video and read what is given there to you. And one of the questions that is asked here that relates to atmospheric pressure is, why is it that people living in mountainous places must use a pressure cooker? Or why are pressure cookers indispensable to people living in these areas here? We want to use these figures here to explain to you why pressure cookers are indispensable to people living in mountainous areas. So this figure A is showing you here that this water, which is maintained at 70 degrees Celsius and is having a pressure of 1 atmosphere, is not boiling. Water will only boil at 100 degrees Celsius when the pressure above its surface is 1 atmosphere. So the point to note is that one of the factors that affect the boiling of any fluid is the pressure above it. So in this case, because the pressure is 1 atmosphere, the temperature of the water needs to be raised to 100 degrees Celsius. And it doesn't matter how much heat is provided to the water, it will not attain a temperature higher than 100 degrees Celsius. Okay? Now look what happens. If we have the same system here with the water at 70 degrees Celsius, but instead of maintaining the pressure at 1 atmosphere, we use now a vacuum pump to remove the air from within the system here. So we're making the pressure above the water here less than 1 atmosphere or less than 100 kilopascal. Now what happens as the pressure is gradually reduced, all of a sudden, at some point, even though the water is at 70 degrees Celsius, boiling takes place. And you see bubbles start to come up here. Okay? So the point that is made here is that the water can be made to boil at a temperature less than 100 degrees Celsius if the pressure above it is less than 1 atmosphere. And the temperature at which it boils will depend on the pressure above the water. The lower the pressure, the lower will be the boiling point of water. So people living in mountainous areas now will have their water boil at temperatures far less than 100 degrees Celsius because of the low pressures that are experienced there. Temperatures much lower than 100 degrees Celsius will not be conducive to cooking their meats and vegetables. That is why now they need to use the pressure cooker that allows the water to attain temperatures much higher than the water up there can be boiled at. Okay, and this other figure here will help us to understand how that happens. Look what happens now. We are doing the opposite in figure C than what we did in figure B. In figure C, we are actually now forcing air into the system here. So we are now making the pressure above the water higher than atmospheric pressure. A thermometer placed inside the water there now shows that the temperature attained by the water is now higher than 100 degrees Celsius. So what is the point being made? The underlying point that can be made is that if the pressure above the surface of a liquid is decreased, then the point at which that fluid will boil, such as water, will get less and less. If the pressure above it increases, then we can allow this water to attain a higher temperature before it starts to boil. And this is the principle that is used in creating the pressure cooker. Of course, the pressure cooker is an airtight container. Let us assume that this figure D is depicting how a pressure cooker works. So here is your heat source. Here is your water and the content in that pressure cooker. As the water and its content gain energy, what happens is this. Water will vaporize and remain above this liquid here. As more and more water vaporizes, the greater is the pressure that is created above the liquid. And that keeps going on as more and more water vapor gets trapped inside here to create a greater and greater pressure. And that allows the water inside here to attain higher and higher temperatures before it starts to boil. So the temperatures that are created inside here now in the pressure cooker are high enough to tenderize the meats and vegetables and allow it to cook faster than if they had to do it at temperatures much lower than 100 degrees Celsius. But question now is this. What happens if this is an airtight container and we keep forcing steam into this part of the vessel here? Obvious answer is that it could cause the thing to burst. So why pressure cookers have a nozzle? That nozzle there is a safety valve. It's a safety valve that allows any excess steam that is produced that will cause higher than a certain pressure that can be withstood by the walls of this pressure cooker to escape. So only a certain pressure can be attained by the pressure cooker. Okay, so that is why at some point you hear your nozzle starting to sing. Okay, that tells you now that, you know what, the pressure that was desired has just been attained. One of the precautions that people must take is this: is to ensure that nothing is impeding the working of this nozzle here. Once I noticed a very dangerous thing in my home with my pressure cooker. The handle of this lid here was over this. The handle of the lid was impeding this nozzle from working. That could have caused a big accident, because if all that steam had accumulated inside here, eventually the pressure cooker would have burst and caused a big accident. So this is something that is related to atmospheric pressure and the applications of atmospheric pressure, and why pressure cookers are indispensable to people living in mountainous areas. Okay, these are the paragraphs here. Speak about how the relative magnitude of the forces of attraction between particles of matter determine their states. Here you're seeing that in solids, these forces are so strong that the particles are in fixed positions. Only vibration of the particles are allowed, and this is what gives them their definite shapes. In liquids, because of the weaker force of attraction between the particles, they are free to slip and slide over each other randomly. Because of this, they take the shape of the containers in which they are placed. In a gaseous state, the forces of attraction between the particles are very weak, and because of this, the particles can diffuse to infinite distances from each other. Of course, these gas particles can be squeezed if they're compressed to give smaller and smaller volume that they occupy. The particles can vibrate, rotate, or translate. Molecules, the bonds between them can stretch. Particles can spin, and they can move from one place to the next. Now we talk about changes of state. A solid becomes a liquid if it is given enough energy to allow its particles to start slipping and sliding over each other. A liquid can evaporate if the particles gain enough energy again to overcome the force of attraction. For example, water vaporizes by the weakening of the London dispersing forces between the molecules and the breaking of the hydrogen bonds that are present. Okay? All right, I hope that was useful. So you'll see you next time when we give a more detailed discussion of atmospheric pressure.